Welcome to the second part of these sessions. So we are very happy we are going to hear the talk provided by the assistant professor Su Hao from UCSD. And he's going to talk about the 3D spatial intelligence. So welcome.
Okay, first of all, it's my great honor to be here to present the talk. Um, um, I think I attended the opening ceremony, which was at the National Conference Center. That's great. Um, now, hope that I will have an opportunity to attend further events in future years. Before my presentation, I'd first like to learn the background of you. How many of you are undergrad students? Raise your hand. Okay, and graduate students? Okay, and faculties? Okay. Great to know. Wondering what is the background, that makes some difference in a way that I present. Okay, so the topic is 3D spatial intelligence. Well, you probably have heard about like this buzzword quite a lot, right? This is getting the attention of not only academia, but also the industry and even the investment. What is 3D spatial intelligence? Well, to me, that's an approach which is using data-driven approach to understand the 3D space. Well, this is a pretty young field. Probably started when I was doing my PhD work at Stanford University around that time. Not only me, but also there's a group of people who are pioneers in a field. And then that was around the year 2010 to 2018. It has been roughly more than 1 decade. Okay, I'd like to start for motivating the topic of why 3D spatial intelligence is important, and then let's revisit the foundational era of 3D AI. Well, that's from my own perspective, which is from 3 papers in my PhD time, and then that's about the flourishing of the field, which is around the year 2008, especially after the publish of NERV work, neural radiance field work, until now. Well, NERV won the Frontier of Science Awards last year. And in the end, I'd like to provide a summary and outlook, which is about like the connection between the 3D spatial intelligence and another very hot topic now, which is embodied AI. And probably along with the presentation, you'll see the connection. Okay, so let's start from the topic. Why is 3D spatial intelligence necessary? This is very easy to argue because we live in a 3D world, right? Our universe is geometric, well, or to the micro level, the molecules are geometric, and to the daily life objects, what we use, what we eat, what we wear, where we're living, they're all 3D. Okay, so we think for artificial intelligence, one of the most important topic is how do we understand, how do we represent, how do we generate 3D data? And practically, 3D understanding gives a lot of applications, right? So for example, the series of work I'm going to present today, they are the foundations for autonomous driving, for robotics, or for the metaverse, which we hope will happen in the next few years, or for medical understanding, or even for understanding like those particles generated in large-scale physics experiments, like run by the accelerators. Okay, so not only are we interested in understanding 3D data, what's even more interesting is like, are humans, whatever we see, which is 2D images, or maybe more than one view, we give it a 3D representation. Our mental representation is 3D. Like, see, this is just a top drawing of a boy standing on the road, but you just can't help worrying for it. The boy, like your mind automatically interpret this 2D image to become 3D. Can we turn off the lights here? Is there a way? No? Keep it on? That's okay. Okay, so see, we see 2D, but in our mind, we naturally convert to become 3D. How does this process happen? If I think, okay, we try to check the shadows, we understand by the occlusions, maybe there are a lot of other cues, maybe brightness change, right? But fundamentally, can we solve the problem by like the very classical approach of, for example, differential geometry or computational geometry? So, but for data-driven idea, it goes to geometry understanding, by the history of math, right? People studies the differential geometry from the infinitesimal perspective or computational geometry from the combinatorial perspective. But it seems like they're not the best tool to directly address such challenges. And therefore, the idea of 3D spatial intelligence, fundamental idea is like, I'll be able to learn the priors out of a lot of 3D data and then leverage the priors to interpret, even hallucinate the geometry out of maybe just pixels from images. Okay. So this kind of 3D spatial intelligence not only allow us, or you should think of it not only from the perspective of reconstructing the geometry world, but also, even more importantly, we think it's the foundation to interact with the physical world. It's like if you're going to build a robot which has a similar level of a general intelligence, whereas people now start to like to say, use the term general intelligence, right? Even though we haven't defined it properly. One of the very important part is you must understand the spatial relationship between objects. Like when the robot tries to manipulate objects, you have to infer the distance between your manipulator and the object and their manipulation. So 3D understanding is so basic. It's a very fundamental cognitive ability of any intelligent agents. Okay, so let's review how this field gave rise, which was the reason that I'm here, because one of my early work at that time was awarded the Frontier Science Award. Okay. So that dates back to my PhD time. I was pretty fortunate. Before working on the 3D data, I was part of a prominent 2D data set that's called the ImageNet data set. So after working on the ImageNet data set, we saw deep learning took off. And we saw like, okay, deep learning is able to leverage very big, very large scale data. But when it goes to 3D, we face new challenges. There are challenges of including like the 3D data are not as rich as 2D, as well as the 3D data have their unique geometric structures, which are not quite like 2D images. So we at the time have to address those challenges. I'm going to revisit them a little bit, okay? So we basically address three fundamental tasks. One is to build large-scale 3D data set. A second is to build the backbone neural networks to understand 3D data, and also think about the representations to reconstruct 3D data. The first achievement at the time was the ShapeNet, which was a very large-scale 3D data set. These 3D objects are, these 3D data are the data of objects, and they are those objects built by artists. So a lot of data were originated from one project that's called the Google Earth. Okay, so Google Earth built some 3D modeling tools for amateurs to be able to quickly build 3D models. Even though in the end, Google didn't use the tool because they were using the Street View, right, which was like the multi-image based approach. Those 3D models as a side product were aggregated together to become a very large-scale free 3D data. At the time, I organized this data to make them a very large-scale 3D data sets. At the time, the ShapeNet data, we in total collect about like 3 million object models covering 4,000 object categories. And before the ShapeNet, the larger data set was playing around a few thousand objects. So, if you want to learn very general object or geometry priors out of a lot of data, such preparation is needed. Well, I'm going to be pretty quick in introducing the data, but I think it's pretty worth some introduction, although intellectually that's not tricky. Okay. So the ShapeNet is a collection of a few million objects organized based upon a semantic taxonomy, which the backbone is the word net hierarchy. So like for each of the word net, it has the images from the ImageNet and also have some of the 3D models from the ShapeNet. And additionally, the 3D mesh as the form of data most closest to our physical space, they have the advantage, we call it like complete and pure. So like all these 3D models, they have the mesh structure, and we're able to easily understand some of the geometry properties, like the physical symmetries, like we decompose them into semantic parts, and parts may be annotated with like dimensions, physical dimensions, the material properties of the mass, which make them to be simulated. And plus, that was also the time of, starting point of a line of approach. It's called a sim to real. Today, in robotics, you probably heard of like the method sim to real, right? So basically, the idea was like you have a lot of 3D objects, and you annotate those 3D objects with materials, with physical properties, with textures, with semantic information, and then you could leverage a computer graphics approach. It's called render, to convert those knowledge to the sensor domain. Like maybe you can sample points on the surface and you get a point cloud. The point cloud is a collection of points on the surface, and annotation of those, each of the point cloud. Those annotations can be texture properties or can be semantic path information. So the ShapeNet actually has a big impact. It's the starting point of a lot of data-driven 3D research, which I'm going to give you 2 examples. Hopefully you find it interesting. And then later it was very widely used, and they become the basis to form a new field, the 3D spatial intelligence. Okay, next, probably I'm going to present some work with a little bit of intellectual strength or merit. So we think about the question of learning from 3D data. Now let's assume that, the learning setup is you have a lot of point clouds. Each of the point cloud corresponds to probably one object. And maybe you want to achieve the goal of maybe doing object classification or segmentation or some additional scene level parsing. Now, we would like to find a neural network to support this end-to-end learning. So mathematically, we face some challenges. Before the work point.net, people think about processing image. A very popular approach is a convolutional neural network, right? So assume that the image is a 2D array, and there is the translation invariance, and this is encoded as the kernels for the convolutional neural networks. However, when you go to the 3D data, the situation is kind of different, because the 3D data, here we call them 3D, but literally they are usually the 2D surfaces that are curved, embedded in a 3D ambient space. So we do not want to do 3D convolution because that's too much expensive. Instead, we'd like to only care about the information on the surface. Now, without this 3D convolution, if I don't allow you to do 3D convolution, but still want you to focus on the surface, you probably have to think of some smarter ideas. Now, one perspective is to look at those points or set of points as a set. Okay, sets means like they are order invariant. Of course, you would also think maybe connect neighboring points so that they become a graph, and then your problem becomes like graph understanding. And therefore, the 3D learning is actually the beginning part of deep learning on a set or deep learning on a graph. They gave the earliest graph neural networks. Okay. I think it's skipped it. Okay, so the question becomes like, okay, I have endpoints forming a set, and then I would like the neural network to be able to produce a signature of the set. Okay, as a signature set, it has to be orderless. Say in a computer, you may save those points, endpoints, as n rows, and each row corresponding to a point. Maybe you have 3D representation x by z. Maybe you would also consider normal that becomes 6D for each point. But if the order of the points changes, your neural network should give you the same output value. And that actually corresponds to the symmetric function, right? So if you have function, then the argument does not affect the function value. We call it symmetric function. And in math, we have so many basic symmetric functions, right? Like in max function, summation function, there are symmetric functions. And then that becomes a question of like, we are basically looking for symmetric functions. And then we're looking for a universal approach to build or to approximate arbitrary symmetric functions by neural networks. Okay. Well, so I think when I was realizing this issue, I mean, then, for the application problem, you start to think about a fundamental mathematical way to address it. And one observation motivated us to construct the broad category of symmetric functions. Now suppose that h is an arbitrary function, and gamma is an arbitrary function, but g is a symmetric function. Can be simple. Then you could easily attest that f is a symmetric function. This is a very intuitive, right? But it does give you some kind of clue. From a simple symmetric function, it's possible to construct complex symmetric function. Okay, and the point net is based upon this idea. Now, suppose you have a number of points, and then you would apply a multi-layer projection, which is a complex function over each of the point, identically and independently. And then you just use some simple symmetric function to aggregate their output. And then use another MLP, multi-layer perception, to transform it. And then the final output, this output will be a symmetric function of the input. Well, obviously, you can claim you are able to construct symmetric functions in this way. But then the reverse question becomes, how powerful is this family of symmetric functions? Would arbitrary symmetric functions be constructed in such a stupid manner? Yeah, so we hope like the set of symmetric functions constructed by the simple way will be very, very large. And in fact, you can prove that this is true. It's like if you would like to use a very large latent space or many dimensions of a latent vector, then you could prove a universal approximation to any continuous symmetric functions. Here, continuity means if you will perturb arbitrary xi a little bit, then the output f is not going to change much. The proof is actually also not complex, but the implication is strong. And further, this construction even allows you to do some interpretation and see in the end, the network is learning to smartly participate the 3D space and check some of the occupancy information aggregated together. I'm not going to dig into the proof, but I'm just telling you that we started from a very basic idea that we would like to combine geometry and statistics, but somehow it's possible to have some interesting results and have a big influence over the application field. So that's the earliest point net architecture. Well, the practical architecture in engineering space is a lot more complex than the theoretical stuff, which is a very deep neural network. And but the fundamental idea to construct it is as simple as before. which is this part is to transform each of the point independently and identically forming the MLP's sharing features. And then this is some simple symmetric function, the max pooling function. Basically, that's the vector level max function, simple symmetric function, and then this is post-processing, and another arbitrary MLP. That was like the point-net construction. Now, this simple stuff gives you very strong performance. Wow, that was like a kind of object classification performance experiment. So we have a data set of a dozen object categories, and then we would like to classify, so each of the category corresponds to point clouds of objects, and then we hope after training, the neural network is able to do the classification properly. So before the point network, there are some other approaches, well, not learning-based or very slow to run. But the point net, using a very simple architecture, was able to perform very strongly. And additionally, it's pretty robust to the missing points. So that work becomes quite impactful in the field with over 10,000 citations as of today. And that's the first neural network to be able to directly process point clouds, focusing only on the surface. And then this one comes with an effective, efficient result. It's not a black box because you could be able to provide a theoretical analysis to it. And also, it's a pioneer work on the set analysis in the deep learning community. Its application includes autonomous driving, but today, like one of my friends joined Waymo and really used the extension of the algorithm to process the LiDAR data running on today's cars in San Francisco. And also, I think I have another collaborator at UC San Diego using network to process those particle data collected from CERN, well, which are from those accelerators. So this is actually a really useful stuff. I'm very proud that it does give you a practical impact. And the third work I'm also going to present, which is at the time when the field emerges. That is, how are we able to generate the 3D data? So I think it started from task 1, a data set. Well, that's labor work. Task 2, which is if you have a point cloud, are you able to learn or process it? And task 3 is, for example, you have one image of an object, are you able to generate a set of points? So this is probably the earliest, among the earliest 3D generative AI models. You know, 3D generative AI is also very hot today. Later, I think I can present it. Again, I think I will very briefly go over this work. That's using a point cloud-based variational autoencoder with a conditional, with a guidance. At the time, the interesting part is we are going to generate a point cloud, but it's not easy to set up a loss function. So for that work, we find, well, if your output is a point cloud, and by supervised learning, you have your ground truth, that's another point cloud, you probably can solve the optimal transport problem. In computer science, it has another nickname, which is called the Earth mover distance to build a loss. So I think that's probably the first work to use such a complex optimization algorithm as a layer of a neural network. We show that it's possible to inject or convert the optimal transport to become a neural network layer and then use it to learn point cloud. And this stuff is differentiable. Here, differentiable means like you're able to compute the gradient of the optimal transport with respect to the location of every of the point. You can usually see that this is actually a piecewise differentiable function. Okay. Here are some of the generation results. Given a single image's input, well, we actually have trained a network from over 200,000 objects, and therefore the objects was able to capture the basic geometry structures, and then, well, when it sees a new, even an object that has not seen it, it's able to predict the point cloud structure. But you can see that was pretty coarse. And you will also see after 10 years of work, well, not less than, fewer than 10 years, I think it's just 80 years of work, people are now able to produce very high quality results. I'm going to show that as well. Okay, so this work also has a good impact. It demonstrates that, it was the first work to demonstrate that complex geometries can be generated in an end-to-end manner by neural networks. And also it shows like classical geometry tool, in fact, optimization tool can be used as a neural network layer. Well, for today, if you look at it, it's pretty simple. But at that time, to me, that was quite open-minded. Okay, so that also inspired the community to start working on 3D generative models. So that was like the early work, 3 of my papers during the PhD time. And then the field, starting from then, took off. And next, I'm going to introduce later, well, some of the latest progress of the field. That's from 2018 until now. Okay, so 3D becomes very prominent ever since then. People find this is a very interesting space, as you are able to invent some neural networks, not convolutional, okay, or convolutional, but have to consider some of the metrics. And then the field of computer vision, when I was doing my PhD time, it was dominated by those detection works, image understanding works. But gradually today is more dominated by the 3D works. And I think I and many others work in the field, and we start to have more and more friends. Okay, I'm going to present, well, that was the time when I finished my PhD and started to become a faculty at UC San Diego. And then starting from 2018 as a faculty, we continue to develop along the 3 lines data, 3D understanding network and 3D generation networks. I'm going to present some of the representative ones. Of course, this is just from my perspective. Concurrently, there are a lot of great works from other researchers worldwide. Okay, so first, again, data. So for AI, data is always so basic. Well, I think my first PhD degree was in math, and my second PhD degree was in computer science. And when I switched to computer science, I was thinking, what's the difference between computer science and math? I guess one of the points is you can't only think and prove. You have to see your data, analyze your data. There are there are some of the phenomena or patterns that's out of your prediction from the data. And that part motivates you to think of a new theory or method to address it. And that's the part about the computer science. Okay, so that's not only about like conjectures, proofs. Okay, that's about like understanding your data. So we always push new types of data to push the field, making further progress. So starting from the time when I became a faculty, there was a motivating question of defining a research topic. I think that we have some algorithms for 3D understanding, and we're able to run a lot of benchmarks. But there's a fundamental question of understanding is not only about 100% and 90%. It's about what to understand. What to understand becomes more prominent than how to understand at the time, around 2018. And then to be able to define what to understand, we must think of a downstream application to motivate it. So robotics or understanding the world for interaction purposes becomes a case. And we start to push the new field that's called embodied AI. And then it becomes like to be able to support robotics or say embodied AI, what needs to be understood? And we think part structure or hierarchical part structure of objects. This is important. Like now, for humans, right, we have to infer this is the part of the cushion to be able to think of how to sit down. Okay, so we start to push those part data sets. Like the PartNet is the largest part-based object database. At the time, out of 20 object categories, we annotated 26,000 models, which gives us 573 part annotations. These part annotations can be thought as the functions defined on the surfaces. And those annotations have a hierarchical structure. We could talk about coarse-grained segmentation or fine-grained segmentation. And we further make those kind of part structures with proper kinematic chains so that they become articulated. There are those kinds of prismatic joints and the revolute joints. And then it's our effort to really give it the physical properties, give them the inertia, right? The frictions, some other Young's modules, some other properties, and in the end become simulatable. So this big turn a lot of 3D models in a ShapeNet database to become the world simulator. And it can be useful to train robotics algorithms. So that's a part of the data. Well, we are then, of course, becoming interested in the part level reasoning of the objects, like part segmentation. Well, and also maybe very fine, detailed, high quality generation. So I guess I would again next present the line of work that we move extend from the point set generation. Okay, so there's a very important work that worth mentioning. I'm going to be very coarse level, introduce this part because it's kind of an extension, give it a sense of 3D spatial understanding. So first, important to talk about a nerve. So point cloud is this place representation, right? The geometries are those samples on the surfaces, but a nerve is an implicit representation. Suppose that you have a point XYZ, and you are observing this point XYZ from a spherical angle theta and phi. You would like to record what are you able to see. You use a neural network to store what you would like to see. And the output becomes like RGB and sigma. RGB is like from a particular view, you see the point in the space with a certain color and also with a certain transparency. That's a nerve representation. This is not my work, very important. What FSA award gave to NERF last year. But this is very important for the field because before that, maybe people were talking about 3D reconstruction, they are using point cloud as I was. But a point cloud, they are coarse. Whereas this neural representation, it becomes continuous. It's like point clouds is just a sample. It's a discrete representation, and this one continuous. This one gives infinite resolution. Okay, however, the nerve have some weakness. Well, if you check the 3D representation of the nerve, you use very deep neural network at the time, like networks of 8 layers. But if you have a very large space, you also want to encode information in a very large space, you find using a single neural network to encode a large space is not a very clever idea. So this work says, let's try to decompose the space into a lot of small voxels. And for each of the voxel, we record the information using the neural field, the nerve. Okay. So that's a very little step from nerve. But for this stuff, the information you stored is highly redundant because every of the cell, especially neighboring cell, in terms of information encoded, they are similar. And therefore, there must be a very smart way to compress what's encoded in a volume. So in 2022, we find that we can approximate the volumetric neural field by the low rank approximation. Well, this is an extension from the classical CP tensor decomposition, and we introduced the matrix vector way. So this approach can greatly compress the information in the volumetric neural field. Here, if you will examine it from the mathematical perspective, I think it's still simple. However, I think in engineering perspective, that's very useful, and particularly that was motivated by our observation that the 3D space is pretty hollow. There's a lot of redundancy, so there must be a way to compress it. And this decomposition is learned in an end-to-end manner combined with the rendering loss and also the local neural field. So this representation makes it possible to continuously encode the space in a very fine-grained manner, and that will give rise to some further very interesting results. Well, you will see them. Next, I think I'm going to present the 1, 2, 3, 4, 5. The 1, 2, 3, 4, 5 is still an image to 3D work. The 3D image to 3D work now takes a single image or a few images as input, and then wants to generate the nerve representation, the neural field representation. And well, later we have an extension called MeshRM. We were finally able to generate the low rank type of volumetric field representation. So this is what we are able to achieve in 2024 using a single image to 3D generation. So that's the input image. Remember, in 2017, we were only able to give you a very coarse point cloud. But after the years, 7 years or 8 years of development of the community, people introduced compressed volumetric neural field so then we tried to generate those compressed low rank neural field, and we're able to give those beautiful results. So you probably could see like the progress of engineering in a field. We have a giant goal, which is high quality 3D reconstruction, which is like in math, right? We want to make a big proof, but we have to think of a reasonable sub-steps. We have to develop techniques, and then you may have to, at the very beginning, give a kind of a proof sketch. But for us, we're also given a sketch that's about the proof sketch, that's about like construction, algorithm construction sketch. And probably you need 6, 7 years working with the entire community to be able to build this. But I think I'm pretty happy to see like, the entire field for the problem of single image-based 3D reconstruction, 7 years we go this far. 7 years, before 7 years, people don't know we can solve it. 7 years, the point 2017, we start to know it's possible to be solved. And 7 years later, it gave it high quality results. Okay, that's a part of a 3D generation. And then about a part of a 3D understanding. I guess, again, you must find a very ambitious goal, right? Here, the ambitious goal is we want to understand the 3D world for robotics purposes. And then we need to have the semantic understanding. That's like, for example, understand the paths with high details. And then the first work tries to address a limitation of the point net. Point net is beautiful in the sense that it's a symmetric function. It has universal approximation to arbitrary symmetric functions. However, I don't want to give a claim that its efficiency for the approximation is low. It's like there is a storage, there's a space complexity, the space complexity is pretty high. And then we want to still leverage some of the local statistical properties to build network architecture so that it's possible to have much better space complexity. And the point net plus plus is along this effort that we will still assume the 3D point cloud or ND point cloud as input. And then we will group the points into local clusters. Within each local cluster, we run the point net to extract a cluster level feature. And then we will lift it in some high-dimensional space. In a high-dimensional space, try to group again and apply the point net again. So that becomes like a point net is used in a local manner and learn hierarchical features. In the end, learn a global understanding. And here, it becomes motivated by the convolutional neural network, although you do not see a convolutional structure. That's, again, leveraging the translational invariance. Okay, so maybe we can skip this one. And there was even further progress that transformers also enter into the point cloud understanding field. And we use transformers. Well, sorry, I think I should mention this way. For point net, it's a very general set understanding tool. You do not assume any set property, basically. It's just a set. And then for point net plus plus, you assume this is a metric space. And therefore, there is proximity, and you're able to group points into local open sets. But that also prevents you from understanding very far away distances, like the long distance dependency between the points were ignored. And transformer allows you to capture the long-term relationship. So we also try to add those long-term relationship ability by the transformer model and build point cloud tokenizers. And in the end, we were able to allow the neural network to give very good local reasoning. For example, here, this is an example where there is a interactive object segmentation. You provide some of the seed points, and then you're able to segment objects into semantically reasonable local regions. And the very last piece of work I want to mention in terms of the understanding 3D objects is the idea of a neural field comes again. Because if you want to analyze the entire space, you could think, in the end, the output format is there's a field about every point in space that are certain information. You can generate this field. So you can try to use the neural field as the basis of the output of a neural network. And if you will also combine it with some other technologies, you're able to achieve the so-called open world pattern understanding ability. Here, open world means arbitrary objects. So along the line, you see, when I started to work on 3D AI, that was like 2013, the tools are only differentiable geometry and the computational geometry. And now we did have invented some new tools allowing us to understand the semantics or to be able to learn strong geometry priors out of the data. Okay, so that's the presentation about like technology advancement. Maybe a very last piece on what are still being developed. One is like the community is building a unified, today people call it a world model, means like it's standing from 3D, it becomes 4D, right? Because there's not only the space, but also the time together. But the harder part is like we want to have a very compact representation with the space and time consistency. Here, space and time consistency means like, if you will, I think it's a little bit of computer science context to explain it, which is the space-time consistency is not the type of a thing. Maybe in a classical physics manner, it's more like if you think you drive a car starting from one location in the city and maybe go for a loop and coming back 10 minutes later to the original point. Okay, you should predict, you should kind of form a global map of an entire space, but not in an explicit Google map way, but in a way that's more like your neurocognitive map. Okay, so you cannot like forget what you observed 10 minutes ago when you come back. So that's the point of the consistency. Okay, So that's kind of like a summary of the collection of work we have done. The point is like we would like to push the spatial intelligence. So today, this field has become the basis of a few important industry. For example, oh sorry, you have to click. You probably know like there are people talking about a metaverse, right? Like creating large-scale digital world. And there are companies working on that, Adobe or Microsoft or Tencent or startups like World Labs and Rodi. They are all the companies working in the field using learning-based approach to create the digital space. And also, it becomes the basis for robot training. For example, my startup, HealBot, works on the problem of building a virtual space. Like this is a real-world conference room at UCSD, and this is our digital twin. So we digitize the virtual space, so the real space using those learning-based approaches, and then we were able to train robots in the virtual environments. That allows you to give it many, many copies so that many robots can run in parallel. And we do reinforcement learning in it, and have a policy, robot manipulation policy that can be transferred in the real world. So that's like an idea that's called a real to sim to real. That's also supported with spatial intelligence. Companies like NVIDIA, like there are two Chinese companies, Galbot, Yinghe, and Zhiyuan, Agibot, right? They're all pursuing this idea. And then Waymo or Tesla, they're all also leveraging these technologies to build large-scale digital twins and to train their either cars or the robots in it. Okay. In the end, I'd like to thank my advisors, collaborators, and also fund providers, especially my PhD advisor, Stanford, Leo Gibbous. And before I went to the US, my advisors, Henry Shan and Li Wei. And also, well, I would say like I'm presenting, especially for the part of the 3D floor, the third section, a lot of technologies. I'm just an advisor, and really it's my students who are doing the hard work and invent those wonderful technologies. And also my collaborators at the different stages. Some of them become professors. Some of them are researchers in industrial labs. And then those who have supported my lab to run. There are a lot of work that needs funding to support and to build a collaborative environment. Okay, that's it for my presentation, and thank you for listening.
Any question?
Yes.
So what does it take for your model for you to extend to space and time to add one more domain?
Okay. Yes, that's a great question. When we talk about like a world model, right? There's not only a space dimension, but also the time dimension. Well, from our perspective, first of all, you think perhaps you still want to use some kind of a neural field to represent. Oh, well, maybe I should start from this perspective. Okay, so in terms of like the 4D, right, space-time, think about the classical physics, right? We learned there's the Eulerian perspective, there's also the Lagrangian perspective, right? Eulerian perspective is almost a kind of a view of neural field. And then if you take the Eulerian perspective, you would think, when the time evolves, the consecutive frames have a lot of redundant information. Therefore, you should think of the clever idea of compressing them. But what's the best way to compressing them? Of course, you can think of like the TensorFlow approach to do some tensor decomposition, but it's over the 4D space-time. But then there's perhaps a more fundamental perspective, which is taking the Lagrangian perspective, which is like, okay, basically across time, there are the objects that's moving. If you think that way, then that becomes like some kind of a point cloud flow. Point flow becomes more reasonable. And therefore, and if you want to address the consistency, probably the flow kind of idea is better. And therefore, it's really, I don't think that I can have an answer at the moment about what's the best representation for the space and the time. But I just feel like, based upon the research that we've done, well, there are the necessity to think of a hybrid representation, both including the particle perspective as well as the field perspective, and to be able to compress and to be able to keep persistency. Sorry, it's not really an answer, just some hypothesis. Yeah.
So, do you think 3D?
Right, that's another excellent question. My takeaway is this. Now, first of all, are we thinking about large time step or small time step? If you think large time step, it becomes highly nonlinear, and perhaps neural networks is very helpful. But if the time step becomes small, with a very small time step, there are a lot of new linearity that comes out. And you want to optimize the algorithm, you will gradually think, you introduce some of the like the scaffolds. And the scaffolds in the end will lead you to the classical simulation algorithms. That's my sense. It's like, for example, what's good about a mesh? If you want to compress to the extreme, you find you care about maybe the surface structure. That's about the mesh. You ignore anything that's hollow in the space, leaving only the solid part. That's about the mesh. So learning definitely is interesting, but for me, I'm more interested in using learning perhaps to be combined with the classical physical simulation. The two may have a good way to interplay and complement each other. A pure learning-based approach without any geometric or physical structures to support it will be highly non-efficient. That's my feeling. Yeah.
Really?
I have a small question.
Yeah, sure.
So, I think in your have shown we are really
Right. Oh yes, it's. You mean? It's data generative model. Sorry, it should be here. Okay. I think. Oh yeah. Do you mean this stuff? No, this one. Oh, this one? Oh, okay. Uh-huh. Yeah, okay. Maybe I can explain a little bit about the difference between this page and this page. So this page is more about like the VR. That's about creating the virtual space, mostly for visualization purposes. And we care about the appearance of an object very much. Well, of course, you still need, basically, you need a learning-based approach for the purpose. And but for the next page, when we talk about robotics, the precise geometry and the physics gets more important. For here, because it's more of a VR or game kind of environment, you need some reasonable physical property, not so faithful. Maybe not your question. What's your precise question?
You form knowledge base.
We form a knowledge base. Well, you need millions of 3D objects as a knowledge base to train your network. Yeah, yeah, yeah.
Yeah. Really excellent work. Also, I will have similar questions, and I'm very interested in the concept, the unified world model. It seems like even become a larger class of AGI in some sense. Yeah. So if you consider we have a unified like a robot to carry out different tasks, what kinds of tasks you think they look different, but in fact it can be simple to do, or inverse? What kinds of different tasks that are really hard to combine together?
Can you
Yeah.
further explain the question?
Like for instance, we hope we have a robot that can maybe like do something like 自动驾驶 or VR or total different tasks. What kind of tasks they look different, but in fact is in fact it's simple, like you can really combine the different tasks together by using
I see.
in one body.
I roughly get your question. When we talk about a task, that's actually very vague, right? What can be a task? Well, there are some perspectives think about that when you go through robotics. First, it's like the time horizon. There are certain tasks with a very short horizon. Maybe pick up the bottle. It's a very well-defined task. There can be another kind of task. For example, clean the table. Well, clean the table obviously is also a task, right? But there are a lot of different ways to clean it. Yeah. And then you may think, I mean, if you take the perspective of reinforcement learning, pick up the bottle is defined by the consequence, which is the bottle goes with your hand and leaves the table, but it's short horizon. And clean up the table, to some extent, you can also think it's a description of the final state of the table that is in organized manner. Yeah, from this perspective, you can actually have a unified definition of the task, which is by defining a reward. But this reward, one is short horizon reward, the other is a very long horizon reward. And when you try to solve a reinforcement problem, it's a very long horizon reward, right? You face the typical challenges of, first of all, this is a very sparse reward problem. And the reward back propagates along a long horizon is hard. And also, you have to address the so-called exploration problem. Because if this is a very long sequence of actions to optimize, there are a lot of local minimums. Probably you think you do this way in a gradient manner at the beginning, but later you get stuck. Yeah, so this is kind of a perspective like by the horizon, short or far. You could also think of perspective, some of the tasks are simple, which is like, we call it quasi-static. This is from a mechanical perspective. Mechanics perspective, right? So once I have established contact between my finger and the bottle, the contact point almost never changes. But there are also some of the harder questions, like for example, using chopsticks. Using chopsticks, you have to constantly change the contact region between your hand and the wooden stick to be able to achieve interesting manipulation. Therefore, based upon the change of the contact, that's different. So for us, when we work on a simulation, that kind of a change of contact is usually caused by deformable objects or soft body. And it becomes a question of, are you able to build good robot simulators or physical simulation algorithms to be able to simulate the soft objects very well? Yeah, well, today's soft body simulators leverage the finite element method, right? Well, usually they're slow and they're inadequate in some of the physical properties. And then, of course, learning can come into play of how are you able to simulate the soft body better. So this is also a perspective task. But I think I can give you some of the dimensions of the task, but you see, task is so vague. Yeah.
Yeah, thank you. Thank you.
Mhm.
One more question if you have. Oh, yeah, please. The pipeline of digital twin mainly consists two parts, real to sim and sim to real. Well, my question is, in your demo, how do you achieve real to sim, such as methods using commercial scan apps or 3D Gaussian splatting, and also in which simulator, like AskSim?
Oh,
Thank you so
I
much.
can first answer the question of the simulator. One page here. Sapien is a robot simulator. That's our work in 2020. And actually, ISAC was built after us. We did something and they think, oh, this is the right thing to do. So they start to also build a simulator. But I still think like our simulator is better. Yeah. Yeah, so we use Sapien as a simulator for task. And then there was a question about the real to sim, a digital twin. So there is the visual appearance part, and also there is the physical properties part, right? Well, visual appearance, those neural fields or those particle-based approach like Gaussian splatting are good. But for the part of the physical properties, that's actually trickier. Yeah, we actually do not use the commodity 3D capturing devices. Instead, for the part of physical properties, we actually like tries to not exactly measure those properties, but tries to use some approach to give a basic range and then do randomization. You probably know about the domain randomization approach, right? Yeah. So that we're able to cover the physical property. It's kind of like when you are trying to pick up the bottle, you see the geometry very clearly, but you do not know how heavy it is. In your mind, there's a certain range. So you have a policy which works well for the particular range, right? Yeah, so that's kind of that, yeah. I think accurate measuring the physical properties to be able to get robotics, that's probably not the right way. Especially consider we have controllers. What's the point of controllers? Controller is like, even if your modeling is deviating from the ground truth to some extent, it's able to come back and close erase the influence of the error. Yeah. Yeah.
And I have a very simple question. How can we get clear and accurate point cloud and depth image? Although we have so many open source code about many papers, but often maybe considering the commercial, so the code about the depth info or point cloud info from the real world sensor like interreal real sense. It is hard for me to find some.
I see.
use.
What is the field you're working in? Your computer vision? Or what?
I'm digital twin for robot manipulation.
I see. I think that first of all, you probably know the Foundation Stereo, right? Foundation Stereo, which is the very latest library that from multi-view images can give you very high quality depth map. You can try that. And also the best paper of CVPR this year, VGGT. Yeah, that's a very strong approach, and you can take a look.
Okay,
Yeah.
Thank you so much.
Yeah.
Thank you for all the questions and answers. So let's end the end. Yeah.